Welcome to Short Talks from the Hill, a podcast from the University of Arkansas. I'm Harden Young, a research and economic development writer. Today I want to welcome Julian Fairey, an associate professor of civil engineering. Fairey's research interests include the chemistry of drinking water disinfectants and environmental sampling. Fairey is primarily an experimentalist working on applied research topics and developing novel technologies to reduce the risks posed by pollutants and sediments in drinking water. He recently led the discovery of a new compound formed by the decomposition of inorganic chloramine disinfectants in drinking water. Julian Fairey, thanks for doing Short Talks.
Happy to be here.
We're going to talk about this discovery in a second. I know that there's been a great deal of interest in this, both nationally and internationally. But first, I just kind of want to set the table a little bit. A big focus of your work is drinking water safety. Can you talk a little bit about how you got into this and why?
Sure. It really started in graduate school at the University of Texas at Austin. And so I did my master's degree with a professor named Ray Lair. He was more on the contaminated sediment side of things. And Ray was about to retire when I was wrapping up my master's degree. And so I needed to find a new advisor. And so I found Lynn Katz, who ended up being my PhD advisor at UT Austin. And her and Jerry Spitell there had a joint project that was funded by the American Water Works Association at the time. That was looking at chloramines, a topic that I've still been working on in the sort of 15 to 20 years since. I really got into this in graduate school at University of Texas and went away from it as I matriculated from there. I went to a postdoc position at Carnegie Mellon University. But then when I came to here in Northwest Arkansas, I realized that there really wasn't anyone doing drinking water chemistry here in the area. The Beaver Water District out in Lowell seemed to be very research forward and really was interested in working with me on the subject. And so that's really where my interest began here at the University of Arkansas and it's kind of developed from there.
As we mentioned, you and your colleagues recently discovered a new inorganic compound created by the decomposition of chloramine disinfectants in drinking water. There's probably a lot of unfamiliar words in that statement. So can you give us a little bit of background on this compound and what led to this discovery?
This compound we first realized that it formed in drinking water in the early 1980s. There was a PhD student at Cal Berkeley that recognized that when chloramine disinfectants decomposed in pure water, they formed this unknown compound. We knew it formed because he was measuring the ultraviolet spectra of the water. And as chloramines decompose, this absorbance spectra increased. And so we knew this compound was forming. There were subsequent studies in the 1980s and 90s, mainly by Rich Valentine out of the University of Iowa, that did a lot of characterization of this compound. They developed ways to form it in relatively high concentrations, which is really kind of the first step in identifying a compound. They were able to destroy it, and they showed it contained nitrogen and chlorine, but they ultimately weren't able to identify it. And so this work really stopped in the mid-90s. And people kind of memory hold this since then. And I picked up on this work with a colleague of mine, Dave Wahman at USCPA in Cincinnati. We were grad school colleagues together at University of Texas about 10 years ago. And so that's kind of where this all started.
And to be clear, when you're talking about a chloramine, you're talking about chlorination, just a regular process for cleaning water?
So chlorination with what we refer to as free chlorine is the most common drinking water disinfectant used in the United States and worldwide. What we're referring to here is chloramination, which stems from chloramines, which are formed from reactions between chlorine and ammonia. And this is the second most common disinfectant used here in the United States in our drinking water distribution systems. And so this discovery pertains to chloramine systems and specifically the decomposition of chloramines in drinking water distribution systems.
And just to be clear, there are some districts or counties in Arkansas that do use chloramines, but it's not by any means used everywhere.
That's correct. The only one I'm aware of in Northwest Arkansas is the Carroll Boone Water District, so they supply water to Eureka Springs in that area. I'm actually not aware of any other chloramine utilities in Arkansas. There could be, but I think most of Arkansas uses free chlorine for drinking water disinfection.
Now that you've discovered this compound, why should we be concerned about it? And why should we not be concerned about it?
Yeah, it's a little bit of a double-edged sword. So first off, we don't know the toxicity of this compound. Those are studies that are about to start here. But the discovery of this compound is important because Previously, chloramine decomposition, we had this unknown in the mass balance. What a mass balance is, we measured kind of the nitrogen before and the nitrogen after, and there was this delta, this unknown difference. And now we think we've determined what this difference is. It's chloronitromide anion. And so understanding not only what this compound is, but how it forms gives us a better understanding of how chemicals that we do know to have health relevance, things like nitrosamines, gives us an improved understanding of how these compounds form. If we understand how they form, we can engineer ways to control their formation or mitigate their formation in our drinking water systems. And so even in the absence of this being a health risk, it improves our understanding of how other possibly harmful chemicals form in our drinking water systems so we can improve the quality of chloraminated drinking water.
And why should we not be completely concerned at this point?
We don't know its health significance, and so it very well may prove to be harmless. The things that are concerning about this compound is its structure. Basically, it has chlorine, 2 nitrogens, 2 oxygens, and it's very similar in structure to a nitrosamine. Like I said before, has known health risks. NDMA is a probable human carcinogen. This is the foremost nitrosamine that forms in chloramine systems. And so chloronitromide anion has a similar structure to nitrosamines. It's also forming at relatively high concentrations in our drinking water distribution systems. Nitrosamines form at nanogram per liter levels. This is parts per trillion. Chloronitromide anion is forming at about 1,000 times greater than that at microgram per liter levels or parts per billion. And so the combination of its chemical structure and the concentrations at which it's forming make toxicity studies important to do going forward. However, these studies may reveal that this compound is in fact innocuous, not harmful to human health.
So in your mind, what are the next steps, not in terms of larger steps, just as a result of this discovery and your role moving forward? Are you going to keep studying this inorganic compound, or are you going to move on to something else? Is your work done?
Certainly the work's not done. There's a lot of offshoots of this right now. What I'm doing in my lab is I'm producing this compound at relatively high concentrations and isolating it. And then I'll be shipping this stuff to people that are doing the toxicity studies. And so I'm basically a production lab for these toxicity labs right now. And so certainly keeping my foot in the door there. We're also looking at the chemistry of this compound, how it forms. One of the things we were interested in from the science study was that it forms at relatively low concentrations in some drinking water distribution systems, like 1 microgram per liter, but relatively high concentrations in others, over 100 micrograms per liter. Our question is, why is that? These types of questions are what I'm used to answering, and so these are studies that are going to be ongoing in my lab over the coming months and years. But I'm also, like I said, kind of a production facility for the people that are interested in the toxicity of this compound.
Let's switch gears here because there's something else I wanted to talk to you about. You have also developed a sensor system to detect the early onset of nitrification events in water systems. Can you tell us a little bit about what this sensor will do and why it's needed?
So this is also related to chloramine systems. And so one of the drawbacks of chloramine systems is that we're basically, when chloramines decompose, not only do they form this chloronitromide anion, but they form ammonia. And ammonia is food for microorganisms. And when ammonia is oxidized by microorganisms, it forms nitrite, which is toxic, and nitrate. And so nitrification is the oxidation of ammonia to nitrite and nitrate. And so what this sensor system does, it's a fluorescence-based sensor system. And basically what it does is when microorganisms start to grow, they release materials into the water that fluoresce. Before water quality degrades, before ammonia is basically oxidized to nitrite, this sensor system, the fluorescence sensor, picks up the activity of these microorganisms and allows an intervention to take place, hopefully stomp out the nitrification event, so prevents degradation of water quality. This was a project that was funded by the Water Research Foundation a few years back as part of a tailored collaboration. We've basically done the development of the sensor system. I think it's now been purchased by a company, and they're trying to develop this sensor system further and actually put it in drinking water distribution systems. Remains to be seen how useful it will be. Of course, it worked in the lab scenario, which is kind of a highly idealized system. It's just a question about whether or not it's practical in drinking water distribution systems.
So it's still in the development and probably won't be rolled out anytime soon.
Still in the development stage. I think it could be useful in terms of monitoring microbial water quality in chloramine systems. As far as I'm aware, it's not being used actively in any drinking water distribution systems. The sensor is still kind of under development in that regard. Sort of the groundwork for the basis of the sensor was done in my work, and that resulted in a patent a few years back.
Julian Fairey, thank you for coming in today. We appreciate having you on Short Talks.
It's been my pleasure. Thank you, Hardin.
Short Talks from the Hill is available wherever you get your podcasts. For more information and additional podcasts, visit arkansasresearch.uark.edu, the home of science and research news at the University of Arkansas. Music for Short Talks from the Hill was written and performed by local musician Ben Harris.